My name is Julian Silverman, and today I'm going to talk about SN2 reactions. So first up, what does SN2 stand for? So we'll break it down letter by letter and then finally number. So first we have the idea that this reaction is bimolecular, which is to say there are two species involved. That here would be the green and the red, as you see here, coming and going from that center carbon at the same time. And that's going to be indicative of SN2. Next we have the idea of the substitution, that's the S here, and it's going to be a swapping or interchanging so that green is going to come in as that red goes out again. Next we have the idea of the nucleophile, right? Phile meaning love, nucleo meaning nucleus here, so that would be the carbon. And the idea here is that an electron-rich species, or our nucleophile, is going to attack that center carbon here that's relatively positive. So now let's see what this looks like in terms of a reaction. So if we're going to look at them compared to all the different types of reactions, these are the different components you're going to look for. On the left hand of the arrow, you're going to look at your nucleophile, which is going to be small and basic, or very reactive in this case. Our substrate is going to be generally unhindered. That's sterically to say that there's not a lot of crowding, right? So that small, basic nucleophile can come right in. And then you're going to see that flipping of that Y for that X in the product, which also has a different stereochemistry, as we'll see. Again, that's sort of the handedness. And then lastly, the leaving group here is going to pop off and then hopefully be very stable in that solution as well. And lastly, be a relatively weak base, at least compared to that nucleophile that we started with. So now let's look at an actual reaction. Here we have an alkyl halide, right? A bromine on there, and then that's going to react with another type of halide, an iodine here, to go to the iodine species here, an alkyl iodide, and then our bromine pops off over there in the end. And so what this looks like when we draw it out, familiar with this notation, we have our pentane here and our bromine to give us 2-bromopentane as our reagent. Then we also have our product, the iodopentane, so again that swapping of bromine and iodine. And you'll note, very importantly, the inversion of that stereochemistry, right? What was the R is now S, and that depends on the transition state in the center. So what happens here is we have a hypervalent carbon, right? There's 5 species on there, so this isn't stable, this wouldn't last for very long. But what's happening is that iodine comes in with a backside attack and pushes out that bromine at the same time. Sort of like a push and a pull happening together. And what we're going to see is again that inversion of stereochemistry as what's behind the board and in front of the board sort of are pushed in the opposite direction. And so one good way to note that you have SN2 is you're going to have that change in stereochemistry as well. Lastly, we'll look at the types of carbons that we're reacting with. You can count here, there's a center carbon attached to 2 other carbons, so that's a secondary, and we'll see how that affects SN2 in just a moment. So let's talk about the different variables when it comes to SN2 reactions. We've already talked a little bit about nucleophiles, or what's coming into that carbon. We have our leaving group, or what's going out. We then also have the nature of the substrate, right? What's attached to that carbon? How does that affect what's going on? And then lastly, the solvent can play a large role in making sure that leaving group is stable. And so let's look at each of these one by one. To start, we'll focus on the nucleophile, again here in green that's coming in. We're going to want a strong base, like I said, so something relatively small, and it can get right in there. That's little steric hindrance, and it's going to be negatively charged. And so the first question you might ask, in the example we just gave, is why would the iodine, which is larger than that bromine, be a good nucleophile? And so what we think about is that these are relatively similarly sized compared to, say, other types of molecules, which are multiple atoms. So sometimes you're looking at either the electronics or the sterics, which is to say either the basicity versus the sterics. And so those are 2 things that you can weigh. Lastly, we'll look at the impact of the leaving group on this slide, and we'll look at the idea that we want that red atom here to be very stable in our solution when we're done. We don't want it to push the reaction backwards, and to be a weaker conjugate base than that nucleophile that we have. So we'll talk a little bit about conjugate acid-base theory as well. Now we'll talk about the sterics of that substrate, which is to say how many carbons are going to be attached to those center carbons. You may remember we have primary, secondary, tertiary, and quaternary. We're not going to talk about that today. We'll look at the fact that SN2 can react via primary or secondary carbons, and generally not with tertiary, as we'll see. So here's an example where we take different types of alkyl halides, but relatively similar, right? They all have that bromine on that carbon chain, and we're going to react with a strong nucleophile here to give us different reaction rates, right? And so comparing, we can see that primary is a faster reaction than the secondary, right? 20 times so. And methyl is even much more so, more than 20 times so. But if we go to that tertiary carbon, like we just spoke about, you're going to see that it's a very, very slow reaction rate. And so those will be reserved for SN1 generally, or perhaps elimination reactions. Lastly, we'll briefly discuss solvent considerations. This is to say we would want a polar aprotic solvent, like acetone, over a polar protic solvent, like water. And the idea is very simple. In our polar protic solvent, we could have those hydrogens popping off and getting in the way, maybe even reacting with our nucleophile. So we want something that's not going to interfere too much. So now let's do a sample question and bring all of these ideas together. We're going to ask which of these substrates reacts via SN2 most readily. And so what we're going to find is it's here a question of sterics and also the leaving group, right? There's no nucleophiles on this page. We're assuming we're going to be doing an SN2. And so let's look first for the sterics. We can see here we have a secondary carbon. Here we have 2 tertiary carbons. And then here we have 2 primary carbons. So we already know it won't be B or D, right? Those are going to not react via SN2. Generally, primary are going to react faster than the secondary that we have here, so we'll come all the way and look at now comparing C and E. And the question now becomes not sterics, but rather the leaving group. So we're going to distinguish between the Cl being a better leaving group and the I, and we know that we want it to be a weaker base. Now generally, I don't remember which is a weaker base, but I do know which is a stronger acid, right? We know that HCl is a very strong acid, whereas HI would not be as strong. So now if we think about the conjugate base, we can see that the Cl here is going to be weaker than that of the I- if they both pop off. And so in fact, we're going to find that C is our answer. Again, not only is it primary compared to the tertiary and secondary, but that leaving group is going to be a weaker base in the Cl- form compared to that I-. And so that pretty well sums up an introduction to SN2. Thank you so much for listening, and I hope you guys learned something too. Have a good